So I will use the wait. Okay, great. So now it's there, and I'm changing my USB.
Right, so hopefully you can, we're going to click it if you want to plug it in, or you can just use your keys.
I can use my keys. Wait. So, oh, it's a little bit
Sometimes it's a
laggy.
little bit slow.
Yeah. Yeah, but I think 2 seconds works. I can just click there.
Yeah, it's just sometimes slightly slow.
Yeah, yeah.
If you stand on the cross, then the camera will focus on you.
Oh, okay. So then I need to keep this normal, is it?
Or you can, oh, it's right here. So you can either sit at the desk and use the desk
Oh,
next to me, or you can stand there.
yeah, I
Whichever. I mean, it might be whichever works.
yeah, I think I can use this one. Test, test. Okay. Oh, I think if I so if I need to look at the notes, I need to hold it. Oh yeah. And I should. Hello, test. Okay, that's okay. Take your time. Carlos. Oh, Carlos. Timing is all yours. Not mine. Yours at the moment.
Well, it's still kind of, it's still underlying some of the solutions that you don't like and other topics that they're finally testing. I'm just bothered about it because I was thinking about one other draft talking about art in terms of, we are going to start to see about post interaction art, and I was thinking if I instrument some of the people have done some stuff on the phone, because they all showed some very good pieces of art, not really high-scale work, evaluations of
Okay,
what they do in
I can
evaluation.
mute myself.
I've got some slides to present.
Oh, okay. So
I was thinking of presenting some of the survey art out here, and next to it more so if you want to make it probably
I mean, if you're doing a survey and you want to consider that as part of the data of the survey, I'm not. I mean, a survey as in, something that that is produces, at least some analytics out of it. Then I'm okay with that. Right?
well, I think in the first place, surveys, it's just kind of the list of things that you randomly got, and then it's done with you are aware of the multi-use points or quality.
Okay.
Sure.
But no option defined, but
So
like
I have to
I'm
read
going
it.
to, I'm going to amend my statement that I gave you, which is name, if you're going to name working groups, that's fine, but then you're targeting this work towards the IETF as advice to the IETF as to
can provide advice.
All I'm saying is
I don't just want it to be, here's a list of stuff that happened, right? It's got to be, there has to be a purpose to the meeting, to the document beyond that, right? If you want to form it as, here's what I think should happen next, that's fine. It doesn't have to be grand, right? But it should say, here's what I've learned from looking at all of these, all of these surveys.
good or bad. That was fairly single-sided, and I think it is extremely dangerous. Such as, come to larger agreements.
But independent submissions are independent submissions are exactly that. You're very single-sided.
No, that's absolutely. So I mean, and I certainly, it's easy to separate this stuff into different sections.
Yeah, I don't mean to tie into knots.
Oh no.
So,
So, I mean, with the energy stuff, I specifically try to stay away from the what should be next steps, right?
well, so then you have to be really clear as to what the work has to be in furtherance of a goal. So what's the goal?
So I think the goal was really, I think would be easy to create the workshop, which the workshop was so important to provide people today know what is happening, so that they don't necessarily repeat what they've already done, right? Also things that IRCs, but
All right, we're just figuring out the technology here. We'll be starting in a couple of minutes.
Here are the paths we've gone down already. All right, then in that case, you have to document in those paths why they didn't proceed or what happened. Right? You can say, here's why it worked. Here's what there was just no consensus, or being as factual as you can. Right? But I got to tell you, the value in that is marginal, right? And the reason it's marginal is because I don't think people are going to listen, right? They're going to say, well, maybe the timing of the idea was okay, but if on the other hand you're much more prescriptive, how are you? Yeah, it's you too. From the extreme south to the extreme north.
well, I mean, I heard a couple of folks who were some started ranking up on the
Because I can show the video.
what I was hoping to right, and
You can see things like basically the idea. This was shown on the technology has moved beyond because and then say this one here deserves a little bit more consideration because I'm sorry to provide that level of analysis, but then that begins to be, I think, something that people are saying, right? So you say, okay, just saying here's what happened without adding some context around it.
no, I think the problem with energy stuff was that there's so many different.
Sure.
And the one big aspect where I think the analysis.
All right, let's get started. Welcome, everybody. This is the IRTF Open Meeting. It's IETF 120 in Vancouver. Can I just do a sound check? Is everything working? Can the remote people hear us?
Colin, the gain on your mic is and the gain on all the mics is too high.
Mita, can we turn the gain down a little? All right, I don't see anything in the chat, but I will assume I will assume the remote people can hear us. Okay, local volume is a little high, remote volume is a little low. But, Okay, so I will get started while Miteko fix the volume here. So saying welcome, this is the IRTF Open Meeting. I'm Colin Perkins, the IRTF Chair. This is IETF 120 in Vancouver. I'll start with the usual reminders. The IRTF follows the IETF intellectual property rights disclosure rules. By participating in the IRTF and participating in this meeting, you agree to follow the IRTF processes and policies. If you're aware of any contributions, so if you're giving the talk or you're commenting at the microphones and you're aware that your contribution is covered by patents or patent applications, then you need to disclose that fact via the usual IPR disclosure process. And we expect you to do so in a timely manner. If you need further information in that, there are links on the slide for the copyrights, patents, and participation policies, and these all apply to the IRTF as well as to the IETF. We also make recordings of these meetings, and in particular, this meeting is being recorded. The recording will go on YouTube after the meeting, and it's also being streamed live. If you participate and you're not wearing a red do not photograph lanyard, then you risk being photographed, although I do not believe there is a photographer at this meeting. But certainly if you give a presentation or if you speak at the microphones, you will be recorded and the recording will be made available online. Also, a reminder that any personal information you gave is handled according to the IETF's privacy policy. And by participating in the IRTF, you agree to work respectfully with the other attendees. And, we place great importance on the code of conduct, so please do make yourself aware of that, make yourself aware of the anti-harassment policies and procedures and so on. And if you have any questions or concerns, please do either talk to me or talk to the Ombuds team as you feel is appropriate. If you are participating in this meeting in person in the room, you need to sign in to the meeting using Miteko, using the on-site tool, either by clicking on the on-site tool link in the agenda page in the data tracker or by scanning the QR code on the screen. If you're in the room and you want to ask questions, please do so using the Miteko tool. We have a common queue for the local and remote participants, so don't just go to the microphone, join the queue in Miteko if you have questions. Remote participants, well, if you can see this, you've already joined using the full client. Please turn your audio and video off unless you're actively wanting to ask a question. If you have any technical issues, mail support@ietf.org or go to the URL on the slide. Okay, so the IRTF is a parallel organization to the IETF, whose goal is to focus on the longer-term research issues relating to the internet, while the IETF does the engineering and standards making. The IRTF is a research organization. It's not a standards development organization. That's the role of the IETF. And while the IRTF can and does publish documents in the RFC series, it publishes informational and experimental RFCs, that's not the main focus of the work here. The main focus of the research groups is expected to be understanding and papers, essentially, research results that get published in the usual academic literature. IRTF is organized as a number of research groups. There's currently 15 research groups. The Gaia Global Access to the Internet for All research group met this morning. Those other groups, which are shown in dark blue on the slide, are meeting later this week. I think we have network management later this afternoon, and then the privacy enhancements and assessments group in the last session today. And then the others listed in dark blue are meeting later this week. The Quantum Internet Group, the Information-Centric Networking Group, the Thing-to-Thing Research Group, and the Computation in the Network Group are not meeting this week, but the other groups are. As I say, the main focus of the IRTF is in research papers and publications rather than RFCs, but we do occasionally publish RFCs, and there have been 3 RFCs published since the last IETF meeting. These are an RFC on the Internet of Things, edge challenges and functions from the Things Thing research group, an RFC talking about application scenarios for the quantum internet, and the Frost protocol from the Crypto Forum research group. I'm also very pleased that we have been able to offer a number of travel grants to support early career academics and PhD students, especially those from underrepresented groups, to come to the meeting today. The slide, I know it's a little small, hopefully it's readable, shows the breakdown of who received those travel grants. We are, as you see, mostly female, non-binary or trans participants, and about 2/3 of them from Africa, South America, and India. So I think we're doing, I think, a reasonable job on diversity. Obviously, we could do better. Obviously, we would like to award more travel grants, but I'm very grateful for the travel grant sponsors you see listed on the slide for their support. And if anyone works for an organization which wishes to fund further travel grants in future, then please do come talk to me. We're very grateful for the travel grant sponsors for the awards we've been able to make. We have also, in the IRSG, the Internet Research Steering Group, been discussing the development of an IRTF Code of Conduct. Now, the IETF has had a Code of Conduct for many years. It's in RFC 7154. But if you read that, it's focused primarily on effective conduct of the standards process. We believe we need a Code of Conduct for the IRTF to consider the effective conduct of research and to bring the references to the anti-harassment policy, the inclusive language policy, the Ombuds team, and similar into a common place so it's accessible and readily available for the IRTF participants. I've mentioned this in the last couple of IRTF Open meetings. I've sent it to the IRTF announced list, pointers to it as well. The document is currently draft Perkins IRTF Code of Conduct. And it is a document which we believe is now essentially done. So I would encourage you all to read draft Perkins IRTF Code of Conduct, send feedback to the IRSG and or to the IRTF discuss list. We expect to be issuing a last call for comments on this document relatively soon, in the next few weeks. If you have comments before that, please do let us know. And please do read it and comment when we issue the last call as well. We would like to get this approved over the summer and in place before the next meeting. Also on the administrivia, I am stepping down from the IRTF chair role at the end of my term, which will be in March 2025. So the IAB is seeking nominations for my replacement. The URL on the slide is for the call for nominations. There's also a couple of links there. RFC 7827, which is a document Lars Egert wrote when he was IRTF chair, talks about what the role of the IRTF chair is, both in terms of day-to-day practicalities and in terms of the strategic role of the IRTF chair. I also wrote a page on the IAB's wiki, which is linked there, which I went through what I've been doing in this job for the last 5 or 6 years and tried to summarize all the tasks I've done to give perhaps a less reflective but perhaps more complete summary of what the role involves. If you're interested in taking over when I step down, please do consider nominating yourself. Please do come talk to me. I'm very happy to talk about what's involved here and to give people a feel for what is needed. And we do need some good candidates, and you know, please do consider volunteering. This is something which would perhaps especially suit a sort of mid-career faculty member, someone who was established, just got tenure, got a bit of time, a bit of funding, and wants to make a difference and have some impact. So if you're interested in that, please do come talk to me. Okay, the other thing we do in addition to the research groups is we run the ACM IRTF Applied Networking Research Workshop. This is taking place tomorrow. We have, I think, 12 full papers this time, 6 lightning papers, and what promises to be a great keynote talk. So thank you to the organizers, Joycery, Simone, and Ignacio, for putting together a fantastic program. I see Ignacio there. Do you want to say anything? Or?
Thank you. I hope to see you there tomorrow.
Okay. So thank you. And as I say, that will be happening tomorrow. And I forget which room. I suspect this one. But do have a look at the agenda and have a look at the papers, which are all online. And the final thing I want to talk about is the Applied Networking Research Prize. The ANRP is awarded to recognize some of the best recent results in applied networking research. It's awarded to recognize interesting new research ideas, which are potentially of relevance and importance to the standards community. And it's awarded to recognize upcoming people who we believe are likely to have an impact on internet standards and technologies going forward. We're very pleased to have 3 fantastic talks, 3 fantastic ANRP prize-winning talks today. Zhejiang Zhu, and apologies, I'm sure I pronounced that wrongly, but Zhejiang will be talking about his work on improving test coverage for network configurations. Yehenia, I'm sure I've done that wrong as well, apologies, we'll be talking about her work on understanding the root causes of DNS resolution failures. And Jasleen will be talking about her work on key transparency for encrypted messaging. As I say, I'm expecting 3 fantastic talks coming up. The papers and the copies of the slides are also on the website. But yeah, we have 3 great talks coming up, and congratulations to all 3 for their fantastic papers. And that's all I have. The agenda for the rest of this meeting, Zhejiang is coming up next, talking about network configurations, and then Yehenia and Jasleen. So, please. Are you coming to it? Okay, so the first talk is by Zhejiang Zhu, who recently obtained his PhD from the University of Washington. His research aims to remedy the reliability risks in the day-to-day operation of network infrastructure, and his dissertation pioneers the use of coverage metrics in network testing and develops the relational abstraction to formally describe network changes such that the correctness of network operations can be checked effectively and efficiently. He graduated recently from the University of Washington and is now working at Meta on AI infrastructure networks.
Thank you very much, Colin.
Thank you.
And hello, folks from the IRTF and IETF community. My award talk today will be about NetConf. It is the first tool of its kind to compute the test coverage for network configurations. And this is a joint work with my fellow student Wei-Xin Deng and our advisors, Ryan Beckett, Ratu Mahajan, and David Walker. All right. It's a bit laggy here, but we'll see. Yeah, here we go. Everyone in this room probably have witnessed a lot of network outages caused by configuration errors. And the consequence was massive, as a small typo could have cascaded into a global scale incident, right? And this leads to the adoption of automated testing to find bugs and gain confidence in the correctness of configurations. research papers have surged, and there are significant engineering efforts going on as well. However, despite that, all major cloud providers have adopted testing in their network CI/CD pipelines. Outages are still happening. Of course, many other things could have made networks run, such as hardware failures, power outages, but even in the part of what we think our tests should have caught them, there are still bugs that made it to the production. One example is the notorious 2021 Facebook outage, where automated testing tools were in place but failed to identify the bug. Now we have a problem. Why would these network tests miss the bug in the day-to-day operations? One may think that the testing tools could be buggy, or the tools were just probably not capable enough to check all different kinds of network properties. These are all true, however. There is one point that the networking community was paying less attention to. That is the completeness of user-provided test suites. Configurations today are large and complex, and a single test only covers a few aspects of them. Imagine if a part of network configuration is not being covered by any test case at all, then bugs in this place won't just be identified, right? Regardless of how capable the testing tools are. So in principle, I believe everyone should be with me that the completeness is better than incompleteness. Then, how well are we doing today, and how can we achieve completeness? These questions are not easy to answer today. Let me try to give you some sense of it via a very simple demo network. Suppose we have two routers. R1 connects to the internet service provider, and it connects to the other router R2 as well. Now, a critical part of this network, of course, is the configurations of both routers. For those of you who may not be familiar with router configurations, they are basically commands and parameters that can control router behaviors in many ways. For example, a router config usually has a section specifying what routing protocols are running on the left. In this case, we use BGP protocol, and the configuration also shows who are the neighbors of this router. On the left, two neighbors of R1 are declared, and for the second neighbor, an import policy is also declared, which I will explain next. So the routing policies are another very important section of router configurations. They are used to customize the behaviors to process the routing information. For example, on the left, we have the policy checks the prefix of incoming routing messages from the neighbor ISP. And if they match a predefined list called internal, then it will be permitted. Otherwise, it will fall through to the next, which is default branch, which will add a tag to the message before permit. And this tag is used by another router to selectively admit routes. If you look at the policy on the right, it matches the tag for permission and then deny all others. Hopefully, this is complex, and hopefully you haven't been lost there. Given the configurations, routers will produce the routing tables, which is then used for the actual packet forwarding, right? Okay. Now, how do we write tests for this network? We write it based on our understandings of what this network is supposed to do. For example, we want to check that R1 is paired with both neighbors via BGP. And this can be done by checking the configuration contents. And we may also want to check that any packets in prefix 20/8 is reachable from R2 to ISP. And this type of analysis is readily available today, which is known as data plane verification. Now, this test suite has ensured that the BGP peering is configured and the connectivity to the internet is good. However, this seemingly good test suite did miss the bug. And because this routing policy, as highlighted in red here on R1, is supposed to deny any routes that overlap with the internal IP addresses. but it is doing the opposite due to a typo. And this bug is serious because these IP addresses correspond to hosts that attach to our routers, and we should already have internal routing paths to them, which is not shown in this figure. However, permitting an external route may override these internal forwarding paths, which will make our hosts with these IPs be unreachable. To be able to find this bug via automated testing, we must realize that this routing policy term is not being tested, and then we can add a proper test for it. Right? An example test would be evaluating this policy term with inputs that have the internal prefixes and make sure that they are rejected at the output of this routing policy. Now, going back to our questions, how difficult it is to know how well an existing test weight is doing for a network, and how difficult it is to write complete tests, right? For this toy network, it may need paying more attention to the configuration details, and it is still doable. But we also need to think beyond this toy example. Our network engineers' daily job is to ensure that the reliability of networks that are of global scale. These are hyperscalers, these are super complicated, and the configurations of them are maintained by a lot of different people, and they evolve at a really fast pace. So creating and maintaining a complete test suite for these tests is just too difficult to be done by our engineers alone, and we need better tools to make this process easier. In this work, we propose to help engineers write more complete network tests with configuration coverage. Given the network state and a test weight, our goal is to compute which configuration lines are covered and which ones are not. And this feedback can help network engineers identify if there are testing gaps. And once they know the gap, they know what is the required new tests to fix the gap. In this way, we can effectively improve the completeness of network tests, which in turn will improve the reliability of our network infrastructure. Next, I'll introduce how we define configuration coverage. So network tests comes in two main flavors. The first type directly analyze configurations, as the test one is doing here. It examines the BGP peer configuration on R1, which corresponds to the line 1 and line 2 as highlighted in blue here. So we can easily define lines directly analyzed as covered, no problem. The real challenge comes from the second type of test, or data plane test. Instead of directly analyzing configurations, they test the data plane states. In other words, the output of configurations, right? If you check reachability, you are not reading the configurations, but the routing tables produced by the configurations. So data plane tests are used a lot in network testing. So when defining configuration coverage, we want to have them supported. And our proposal is that by testing a data plane state, we are indirectly testing the configuration lines that contribute to the production of this routing table entry. We define the contributor lines as the coverage. Now we need to define who are the contributors to a data plane state. As we know, in a distributed control plane, a piece of routing information is shaped by each and every hop along its propagation. In this example, a route is propagated from left to right, and router 1, router 2, and 3 have policy terms that add a community tags to the route, which are used by the router 4 to admit routes. If this route is tested on router 4, the local policy term is, of course, a contributor line because it admits the route. But beyond that, we find the policy terms on the previous hops just as important as the local one, because if they haven't added tags along the way, the tested route won't be derived at R4, right? So we define contributor as lines who are critical to the existence of a data plane state, regardless of its local or non-local routers. Therefore, the key problem that we are solving in this work is to efficiently map any given data plane state back to its contributor configuration lines. And this is effectively a provenance tracking problem. To motivate our approach, we describe two strawman solutions. The first is to do a full data plane simulation and record the contributions at each step. This will do a lot of unnecessary computation. Ideally, we want to compute contributions on demand and only for those who have been tested. And this on-demand provenance tracking has been done in the field of deductive databases. However, it is hard to achieve both fidelity and performance if we encode the whole control plane simulation as deductive clauses. So our solution is based on an insight that the network state often hints the contributors themselves. Assume we have attested RIB entry from the previous example, and we don't know anything about its contributors yet. But this entry has a protocol field indicating that it is from the BGP protocol, right? There is a source protocol field in the RIB that tells us that. Because based on control plane semantics, this route then must have been derived from a BGP announcement sent by its neighbor. And it also hints that which neighbor it is, because the next hop is R1. So we can guess that this BGP announcement is sent from R1 to our router. Besides, a BGP route must depend on the BGP session between R1 and R2 being established, right? And moreover, we should also count the import policy that is used to admit this route. And further, we can keep working back and find the contributors of this first level contributors. In other words, the grand contributors. For example, the BGP announcement must come from a BGP route owned by the neighbor, and the BGP session must come from the BGP peer configurations at both ends of the session, right? In this way, we can infer the contributors on demand, which means that we work backwards from a tested data plane state and step by step, and ultimately discover all contributors. As you may have noticed, this forms a graph structure. The edges are contribution relations, and the vertices are the entities in a network, including data plane states, configuration elements, and some auxiliary concepts that help bridge the contributions. So this is the core idea of our approach. We systematically model network contributions, use a graph-based model, and we also proposed an efficient algorithm to infer contributions on demand. If you would like to know more about it, our papers talk more, and our implementation is open source. Please feel free to check them. Next, let's talk about the design. So we designed our tool to take configurations, data plane states, and test traces as input. And we have implemented netconf to work with the open source configuration testing tool, Batfish, which produces these data plane states via simulation. In concept, netconf could also support tests in live networks or emulated networks, as long as we have configurations and routing tables. Now I'm going to do a live demo of the coverage results produced by netconf. This visualization is based on open source code coverage tool called lconf. As you can see here, we show total lines versus tested lines in the overall project on the top right corner of this report, as well as the computed coverage rate of 26.1%. And then I'm going to click the button And it allows us to browse into the directory and show the coverage of individual router configurations. As you can see, we have 10 different routers in this folder, and we show the breakdown coverage of each of them. And what's coolest is the next. If we navigate into a source file, we can view coverage results as colored annotations on sources. It is very convenient then to view and figure out whether there are lines you care about which is tested or not, and you will be able to find any surprising testing gaps. All right. Let's go to the next. Okay, in the remaining several minutes, let's take a look at how we can use netconf to help write better test suites. The network we will be looking at is Internet 2, a national backbone network in the US. It has 10 BGP routers and over 19,000 lines of configurations. We adapt from the route views project dataset to know the route announcements received from more than 200 external peers. So how would you test this network? A prior word called Bagpipe proposed 3 verification properties for this network. We adapt them into tests using the Badfish APIs. So the first test, block to external, checks that if a BGP route has a specific community tag called block to external, then these routes may not be announced to any external peers. Then the no margin test checks that if a received BGP announcement had a specific prefix within a range called the margins, they may not be accepted, right? And the third, route preference checks that if multiple routes to the same destination were accepted from multiple external peers, the Internet 2 may not select the one from a less preferred peer. So these 3 tests consider the BGP routing behavior from 3 different aspects. So how well are they checking different aspects of the configurations? Let's see what netconf tells us. Oops. The 3 tests collectively covered only 26% of the lines that are supported by our tool. And these 3 individual tests covered 0.6%, 0.9%, and 24% respectively, which means that the majority of the configurations are being completely untested. So this is surprising to us at first. And if this is surprising to you as well, you're welcome to try netconf on your own network to see what's happening. And you can potentially join us in an effort to start an IETF work group to standardize configuration and put it to more usage. All right. The existing tests may have low coverage, but no worries. We can use netconf to make it more complete. Here's an example. So the no margin test we just viewed from the previous slides is about the import policies of Internet 2. So when we look at the import policy to find the testing gaps, we can, by viewing this like colored annotation on source, we can immediately figure out that there are 5, if you can, sorry, I think it's a little bit blurred, but basically this is a routing policy that has 5 terms. And out of these 5 terms, there are only 1 that has been tested, which is marked green here. And this term is called block margins. And there are 4 other terms that are marked as red, which means that they are not covered. By viewing at this result, we can immediately figure out that, okay, probably we need to add tests to check that these 4 other classes of redundant traffic are being rejected as well, right? So based on this knowledge, we add this test and test it again, and the result will show that all these lines will be marked as green. So in our study, we made 3 similar attempts to this, which improved coverage from 26% to 43%. It is far from perfect, but for a network with 19,000 lines of configuration, we can expect a complete test with just 6 tests. With netconf, we now have the visibility to our progress for the first time and a viable path toward 100% of coverage. All right, to conclude, complete network testing is hard by users alone, and it is impairing the reliability of the network. To this end, we define and compute configuration coverage. A key problem here is to efficiently map data plane states back to contributor lines, and our approach is via a graph-based model and an efficient algorithm to infer contributions on demand. And finally, we show that the feedback provided by netconf can effectively make network tests more complete. Okay, now I'm going to take 1 minute to talk about the next steps. So over the last decade, network testing and verification have evolved significantly. All large cloud providers have built such tools internally, and many companies have offered this capability commercially. So these testing and verification tools are built on different technologies, and we lack standard metrics to guide engineers in choosing the most effective tool or technique and understanding the extent of protection provided by them. So during this IETF meeting, we are proposing to initialize a work group effort to bring configuration coverage to standardization. If you feel interested, please join us as an informal discussion during the break session later, just outside of this meeting room. And you are also welcome to contact us offline. I'll stop here. Thank you for listening, and please feel free to ask any questions. Thank you.
Thank you. All right, thank you. Fantastic talk. Are there any questions? And Jana, first of all, and then we'll go into the queue.
Thank you so much. Jana Iyengar, Fastly. Thank you for this talk. It was a lot of fun. As you were describing how you do have the data plane simulated, and then you use that as a way, as the premise, I would say, to test what part of the configurations are being used. It occurred to me that you could extend this to generate configurations. Have you thought about that?
Yes, that is a great question. So coverage, are you talking about coverage guided test generation?
Basically, yes.
Yes, indeed. And we have think about that, yes. And we find that it can do part of the job, yes. But what it cannot do is to generate the assertions, which is the intents of what should be tested, right? And that should be filled by engineers like by hand. So yes, it can do the job, but it can only do a part of them.
Isn't your data plane itself the assertion?
So we can generate tests by looking at what exactly this data plane does.
Right.
But it cannot be used to find bugs inside itself, right?
That's true.
Yeah. Yeah. So that's our view on it. Yes. Thanks.
Got it. Thank you.
Yeah.
Okay, Jonathan.
Jonathan Hoylands, Cloudflare. So I wanted to know why you're not using, oh, sorry, not why. This seems like the kind of thing you would use formal methods for and get perfect answers rather than trying to do test coverage, right? And Bagfish, I know already, is a formal methods tool. So yes, it doesn't check the lines that can't possibly cause problems, but why is it useful to check the lines it knows can't cause problems?
You are talking about why we need 100% coverage? I mean,
well, it's why is tests a good choice here at all, right? Mm-hmm. What I want is not tests, it's mathematical proof that there's no problems, right? Like tests, it's like, well, you hit that line, but you didn't hit it in the right way, so it doesn't count.
I see. So if you're talking about coming up with a complete verification or proof that the network is doing correct, I think you are basically falling into the same trap that your formal properties that describe the network intent may not be complete. And that's
sure.
Yeah.
But your tests also aren't complete,
yes,
right? Even if you hit every line, that doesn't mean you've caught every logic bug.
Indeed, indeed. So that's our positioning. So basically, we are initializing this effort to help both the completeness of tests as well as formal properties, which it doesn't support a lot of verification right now, but we are hoping that in the future it can be extended. And we are very aware that as similar to the philosophy of software testing, 100% coverage doesn't mean that it is bug-free. But it is,
Exactly.
but it is at least that if the coverage is low, then you are in trouble, right? So it's our positioning.
But yeah, because I just thought it was a little bit unfair to say Bagfish doesn't cover all the lines, because like part of the formal methods thing is it doesn't cover the lines that it knows can't cause problems. So like it's
Yeah.
not useful to cover those lines.
Yeah, indeed. Thank you.
And I guess come to Jonathan's usable formal methods research
Oh
group
yeah, and
later
come to
this
my
week.
research group. It's fun.
Lawrence.
Yeah, thanks a lot for the talk. Very good work. Actually, my question is partially covered or addressed Jana's point and previous guy. I mean, because at one point you mentioned that you are building a kind of a graph based on the contributors.
Mm-hmm.
Because my question is you address a lot about the syntax of the bugs or non-coverage. Are you also looking into the semantic? I mean, addressing what we will call intent about the logic. But having a graph can be also a way if you can run some inference, or could be also a tool that you can use to actually detect some of the logic that you want to test. So are you using that? I mean, or is it part of what's coming next?
So I am not have a full picture of a good answer to your question. So basically, what we are doing here is indeed just checking like syntax. I mean, the lines, but we have not yet got a full understanding of what should be the semantics of a network. So we have another work that you may want to check out that checks what are the forwarding paths, what are the network interfaces that have been checked, that have been covered by a network test suite. I'm not sure if it answers part of your question that what about it, what are the semantics of the network that have been covered? But can you talk more about what are the semantics
Yeah,
that
so if I can reformulate, I mean, if you write a configuration, you have an intent for something to happen in a network.
Mm-hmm.
Okay, you put a rule or something.
Mm-hmm, mm-hmm.
When you do your test coverage, you say,
Mm-hmm.
okay, I checked that this configuration, I looked at it. But you cannot say if it's right or wrong. I mean, so is the configuration right or wrong? And can you attach that to your test coverage to kind of,
Got it.
I check the syntax is
Got
okay,
it, got it.
but now
I
I need
see.
also to check if the intent of the configuration is not creating issues.
Yeah, let me rephrase that. So by talking about the semantics of network, you are talking about a list of network intents that is written as the semantics of the network, or as how the network is supposed to do, right? And yes, I think hopefully this work can be extended to compute coverage for that. But actually our question is, how does that written specification be created, at the first place? We haven't seen that actually. So I know some of the hyperscalers are doing that probably internally, which is, aligned with the intent-driven network, the paradigm. But it is not something that is known to our research community yet, and we haven't been able to put our hands on that.
Okay, happy to follow up later.
Yeah, thank you for the question.
All right, one last question quickly, please.
Yeah, Alistair Winmany. Have you thought philosophically about whether you think this is actually a good thing to be doing? In the sense that you'll probably find a lot more problems, but you'll then lull test engineers into a false sense of security. So you will have more CrowdStrike-y type events where everybody thinks everything's going to go well. You don't have enough people in the ops centers because things are going well. And when the excrement does hit the fan, then things are just going to be really bad because you don't have enough people to fix it. Have you thought about that?
So is this question about pursuing a high coverage would will consume more our engineers' times and make things slow?
No, because if you make it better, then management will say, oh, I can save people in operations because I don't need so many people. So that when something does happen, they actually needed a lot more people because the disaster or the blast radius is a lot larger than it is. You might be better off with lots of small. So this is the chaos monkey principle. You actually want noise in networks so that people are fixing it, as opposed to going for perfection and then a big problem taking you out at the knees. So I just think it's an interesting philosophical thing to think about.
Thanks for the great question. I think the assumption of this work is always to try to reduce the outages, but we really haven't thought about what comes after we reduced the possibility of outages. And I think that's a good discussion, but since I haven't been thought about that yet, I think that's welcome to take it offline and have a more fun discussion. Thank you.
Thank you. And thank you for a great talk. All right, I'll just set up for the next. Do you want to use the PDF? Yeah. Do you want to use the microphone or do you want to sit here? Okay. Just use the arrows. Yeah. All right, so our second prose talk today is Yevhenia Nosik. I'm sure you can tell me how to pronounce that properly in a second. Yevhenia is a final year PhD student at the University of Grenoble-Alpes in France, and she works on DNS and network security from a large-scale internet measurement point of view. Her talk today is on extending DNS errors, which was from what, IMC last year? Yes. So over to you.
Thank you for the introduction, Colin. So yes, the paper I'm going to present today was originally published last year at the Internet Measurement Conference with all the measurements done in early 2023. But things have slightly changed ever since. So in this talk, I'm going to give you the updated numbers from this month. But what hasn't changed since last year is that DNS is still one of the main components of the internet, because essentially we have so many services that rely on translating human-readable domain names to IP addresses or the other way around. So this figure here is, of course, a very simplified view of how it looks like, but it does show some of the main components. So usually what's going to happen is that we have some client on the left that would like to get the IP address of example.com domain name. So the first thing it does is that it contacts this recursive resolver, and if the answer is not already in the cache, then the resolver will issue a bunch of queries to different name servers until it reaches the name server of example.com. And then if everything goes well, the final answer is sent back to the client. Now, as I said, if everything goes well, because even in this very simplest scenario, pretty much everything can break. So one thing we can imagine, for example, there is some typo in the zone file, and because of that, the software did not manage to load it correctly and serve the zone to end clients. Or maybe the zone file has some expired DNS sec signature, so validating resolvers would return a server fail. Another thing can happen is that the software refuses to process our requests due to some internal policy. Let's say if we reach a closed resolver, but we're not on the ACL, then in that case, we're getting the refused response code. And then even if for once it is not DNS, maybe there is some underlying connectivity problems. And in that case, we would not be able to communicate with any DNS server over there. So of course, it's not that unusual that things break on the internet. But the important question here is how does the end client know whether something happened and whether the resolution failed? So since the very first day of the DNS, there is this mechanism called R codes or response codes. Essentially, it's a 4-bit field in the packet header with 6 values that were defined in the in the original DNS RFC, such as form error, serve fail, no error, and the remaining 6 were reserved for future use. Now, at some point, we needed to grow beyond this 16 values. So response codes would start appearing in OPT, TSIG, TKey resource records. But that's also when things started getting slightly more complicated. So for example, this response code 9, it has 2 different meanings. It's either not authoritative or not authorized. And this response code 16 was assigned twice by mistake. But in any case, if you're used to dealing with DNS failures on a daily basis, most probably you see quite a lot of serve fails. This is a very generic response code that can be behind unresponsive name servers, lane delegations, DNSSEC validation failures. So in this case, how does the client know why exactly this resolution failed? And it turns out that the answer can be provided with extended DNS errors. So what I'm referring to here is this proposed standard that appeared 4 years ago. So originally the idea was to provide the mechanism to give more background as to why DNS resolutions fail. But more generally, it's a generic mechanism to provide some more context to DNS messages, even if they do not necessarily fail. And also to make it clear, extended DNS errors exist independently from response codes, and no combination of the two is prohibited. So we're not in the packet header anymore because extended DNS errors rely on EDNS 0. And this is how the option looks like. It's option code 15. And the 2 main contributions of this RFC are the info code and extra text field. So if we go to the previous example with the serve fail, now thanks to extended errors, we can actually see what happened. So first of all, we have this info code 7, which says that DNSSEC signatures have expired. But then we also have some extra text between parentheses, which provides us even more details as to what happened. So in this case, Cloudflare tells us, it gives us the ID of the DNS key that caused the problem and even the expiration timestamp of signatures. This extra text field is implementation dependent. So some implementations will give you very detailed info, others slightly less detailed, and some software can leave it completely empty. Then as for the info codes, there is this registry maintained by IANA with 30 entries as of now. 25 of them were defined in the original RFC and 5 were added later on. So these error codes are not really subdivided into groups, but looking at those, we can say that we can see that some of them deal with DNSSEC validation failures, others with response policy zones, caching, software operation, and other aspects of the DNS. These are also considered one of the best practices these days to run for those who run public resolvers. And it's, for example, one of the recommendations published in DNS Resolver recommendations that recently appeared at RIPE. So one thing we wanted to analyze in our paper is how is the standard actually implemented these days by public resolver operators and open source software vendors. So to do so, we have chosen 9 different systems. There are 5 big public DNS resolvers and 4 open source software vendors. So speaking about the changes from last year, this time we include Google DNS to our tests because at the beginning of last year, it did not yet support extended DNS errors. Then for the test cases, what we did was to create 63 different subdomains under extendeddnserrors.com. So those subdomains are either completely misconfigured or represent some of the corner cases. Now, the great majority of them would be dealing with DNSSEC failures because, after all, we have quite a few extended DNS errors that represent those, but we also have a bunch of link delegations there. And then as for the methodology, it's very simple. We just send the DNSA request to every tested system, and then we analyze the response and check if there is an ED code inside and which one. So having done this test a couple of weeks ago, there seems to be something weird with OpenDNS because apparently all my queries resulted in the ED code 16, which means censored. If you look at the definition of this extended DNS error from the RFC directly, what it says is that my domain name seems to be on a block list due to some external requirement. So what we can do as well to see what happens here is issue a simple test with the dig on commands line. And now looking at this TXT resource record in the additional section, we can actually see what happened. So apparently, OpenDNS does not serve customers in France anymore just due to some court order. And that's because that's where I'm based, together with my measurement name server. And that's the reason why I got refused and ED is extend censored in response to all of my requests. So this is just one of the examples of how EDs are used today. Also, in this particular case, we saw that the exact reason for blocking was provided in the TXT resource record, but there is also this draft in the DNS operations working group, which tries to structure the extra text field for those cases when there is a filter in place to explain what exactly happened. So maybe in future, there will be no need for that TXT record. But anyways, after having repeated all the tests from different vantage points in a different country, overall with our subdomains, we managed to trigger 18 unique extended DNS errors from all the 9 tested systems. So the natural question here is to what extent those results are consistent. So what we saw is that only 3 test cases resulted in the very same result, which was no ED at all. So there are 3 subdomains, valid one, which is our control subdomain, no DS, which is a signed subdomain without the DS record published as a parent, and the unsigned domain, which is no DNSSEC signed at all. So for those 3, we did not receive any ED code at all. So what we can do to make such a comparison more fair is for each subdomain, we will compare EDs between themselves and ignore those cases where nothing was returned. So we see more consistency with this approach. So if we want to analyze those systems that actually returned extended DNS errors, they agreed in 14 test cases out of 63. So those test cases were mostly lane delegations, but also 3 subdomains, which represent some DNSSEC misconfigurations. So the natural question here is, why do we see so many inconsistencies? And we identified 3 reasons for those. So the first reason is that not all the 30 EDS codes are implemented by all the software we tested. So for example, with our test cases, we did not manage to trigger any EDs that is supported by bind9, for example. The second reason is that some of the extended DNS error codes tend to be very specific, but others are much more generic. For example, talking about DNSSEC failures, we have this EDS6 DNS bogus, which was returned by at least one system for the great majority of DNSSEC misconfigured subdomains. So while some tested systems would go very precise and say, for example, signature missing or signature expired, others would return a more generic DNSSEC bogus. And the third reason, sorry, is that some of the EDs, they do not signal errors, but rather resolver capabilities. So we had 3 subdomains assigned with 2 very old and one of the newest DNSSEC algorithms. And in those 3 cases, Cloudflare returned ED1, which was unsupported DNS key algorithm. So in this case, Cloudflare did not signal any misconfiguration on our side, but rather it provided more context to the resolution by saying that it does not support those algorithms. And the reason why it's important to talk about those inconsistencies is this recent proposed standard that appeared a couple of months ago. So the idea of the standard is that if we have a resolver that is ED compliant, it may choose to send reports to some monitoring agent that was specified by the name server operator. So if the name server operator receives several reports from different pieces of software with different extended DNS errors that still point to the very same problem, then the name server operators need to carefully interpret those reports. So the biggest advantage of those extended DNS errors is that we can get all that additional info without having to send any additional packet at all. So the next thing we were wondering about is whether we can use EDs to look for misconfigurations at scale. So the methodology will be quite similar here in the sense that we still send DNSA requests and analyze the responses. But this time, what we're testing is not just 63 subdomains, but almost 300 million registered domain names. And we're using Cloudflare because Cloudflare Resolver because it provides very detailed descriptions of what exactly went wrong in those extra text fields. And they returned us the highest number of unique ED codes during the previous experiments. Having done all those tests, overall almost 20 million domain names in the wild trigger at least one ED. We have 19 unique EDs in total, but as many as 215 combinations of different extended DNS errors per domain. So looking at those that appeared most often, this ED22, no reachable authority, essentially what it means is that the recursive resolver could not reach any of the name servers for a particular domain name. So in this case, if we receive a serve fail, now that we know that none of the name servers of example.com were reachable by the resolver. The second most common extended DNS error was a network error. So this error means that there was some problem in communicating with name servers. And here in case of Cloudflare, it provides a very detailed explanation as to what exactly went wrong. So we literally have the IP addresses of name servers inside that extra text field. And the response code that Cloudflare saw on its site. So this is usually something we would not see as an end client. Actually, these two error codes, 22, 23, they mostly came together. And in fact, it was the most common combination of extended error codes. So what it really means in this example is that ED22 says none of the name servers were reachable because ED23 precises that the queries to the name servers timed out. Now this extended DNS error codes is supposed to be returned by name servers if they receive a request for a domain name that they're not authoritative for. But we received it from Cloudflare, which was a bit unexpected in this context. But long story short is that if we send a request not to a recursive resolver, but directly to the name servers of this example.com domain name, it's actually that name server that returns this ED20, not authoritative. And what Cloudflare did was that it forwarded this error to the end client, to us. So in this example, we see that extended errors are not only generated by DNS systems, but they can also be forwarded from one system to the other. And these three most common EDs that we have seen so far, they all refer to lame delegations. Essentially, these are the situations when some name server is delegated to provide name service for a particular domain name, for a particular zone, but it fails to do so. And looking at the extended DNS error codes returned in the wild, this was the most common problem that we encountered. Looking at the most extreme example, as I said, sometimes we get multiple extended DNS error codes for a single domain name, and we saw up to 5 of them. So looking at this first error code, ED9, it looks like there is some problem with DNSSEC because we see DNS key missing. But then if we look down the list, what we actually realize is that the name servers are not reachable because they are not authoritative for this particular domain name. And the resolver is not able to retrieve the DNS key records. That's why it reports DNS key missing. Now, this was an interesting case because we saw a couple of millions of domain names that triggered R6 missing DNSSEC signatures. But for some reason, the resolution did not result in a DNSSEC validation failure because we still got no error in those cases. So looking at this extra text field, it tells that there is some problem with the key with ID 1253 at the .at zone file, at the TLD. So if we look at this very same domain name with DNSVis, what we can see is that there are actually 2 key signing keys, but only one of them is actively used to sign the zone and to establish a chain of trust. So we did contact the TLD operator, and they confirmed us that the second key with ID 1253, it's a so-called standby key, and it will only be used in case some emergency key rollover is needed. So in this case, it makes perfect sense that Cloudflare reports to us that no signatures were generated with this key, but the thing is that it was not supposed to generate any signatures. So we also asked Cloudflare whether it was expected behavior or not. They told us yes, and they also extended their documentation saying that if we receive this extended DNS error without the serve fail response code, then most probably there is some key rollover in progress, or there was some standby key in the zone file. So I will not be detailing all the errors we received for those 20 million domain names. We saw pretty much everything that could have been reported. For example, expired signatures, bogus DNSSEC, DNS keys missing. But still, we can clearly see that one of the most prominent problems that we see is lame delegations. So 4 years after this RFC appeared, we can conclude that it is supported by major public resolve providers and software vendors, and they all managed to identify the root causes of DNS failures, but with different levels of specificity. Some of them return us a very detailed descriptions as to what went wrong, others go more generic. So we also saw that it's very efficient to look for misconfigurations at scale, and we believe it's a very promising technique for DNS troubleshooting. Thank you very much, and I'm happy to take any questions.
Okay, thank you. So does anyone have any questions? All right, well, while people are thinking of their question, obviously, when you did the in the wild study, you found a wide range of types of failures, and I was wondering. I mean, it seemed like a lot of them were sort of the sort of transient failures that you might expect. Do you have some feel for what fraction are sort of transient failures which don't really indicate a problem with the DNS, just the network failed in a transient way, versus what fraction indicate more systemic configuration issues with the DNS?
So actually, to really answer this question, what we would need to do is to run at least 2 scans sometime apart, maybe the next day or even 1 hour later. The results will be different for sure. So yes, speaking of those lame delegations and unreachable name servers, I assume that some of those are transient network failures. But also the lame delegations are a very well-known problem that has been there for a while. So I also expect a fraction of those to be constantly present there.
Okay, so further measurements needed.
Yeah.
Okay, Matt.
Yes, I'm wondering if there's any pushback from people who might have been using obscurity as an additional interference for hackers in not being too specific about error messages, particularly about various types of authentication failure. I mean, for instance, telling which ciphers are not supported potentially opens windows.
So speaking about the security aspect of those errors, there are 2 things to keep in mind. At least the first one is for those systems who generate extra text fields, they need to ensure that they are not saying too much. And then about the fact of returning an extended DNS error itself can also reveal some information. For example, if you're a resolver operator and you have a domain name on some block list, you may or you may not want to disclose it to your end clients. So in this case, you may choose to return one of those response policy zones extended DNS errors, or you may choose not to do it.
I guess I have one other question. I mean, you're at an IETF meeting, and you've been spending a lot of time digging into extended DNS errors, RFC, and a bunch of other DNS RFCs. Is there anything you think the IETF should be doing which they're not doing in this space, or any glaring things you would want to see different in these types of standards? What can we do better?
Speaking about this particular standard, I have found it very clear. It was approachable for me to read it, understand it, and then to measure it in the wild. So regarding this particular standard, I do not have any comments, really.
Okay, good. It's good that we write some RFCs which are clear. Glad to hear that. All right, do we have any other questions? Okay, anyone remote with questions? Let's see anyone in the queue. All right, in that case, thank you very much. figuring out the technology here. Is that everything? Yeah. All right, so the final talk today is by Jasleen Malvi. Jasleen is a PhD candidate at UIUC working on applied cryptography. The various tools she works with have broad uses, but the application she's most interested in relate to secure and private identity on the internet. One direction of her work has to do with bootstrapping identity credentials in a legacy compatible manner. The other deals with individuals identifying each other in encrypted messaging apps. And to that end, she's collaborated with researchers at Meta and worked on an open source key transparency implementation for WhatsApp, which is based on her work, Parakeet, which she'll be presenting today. So over to you.
Thanks so much, Colin. So I'm presenting Parakeet, which is a sort of contrived shorthand for practical key transparency for end-to-end encrypted messaging. And this is joint work with Lev and Alberto, both of them at Mistin Labs, Aisha Ghosh at MSR, Erjan Öztürk, Kevin Louis, and Sean Lawler, all of whom are at Meta. So by the way, there is already a key transparency working group. They're meeting on Friday afternoon. I know what a drag, Friday afternoon, but if this talk interests you, that working group might be an interesting place to go. And in case you are not familiar with that working group at all, then maybe you also don't know what key transparency is, but I'm sure everybody here knows how end-to-end encrypted messaging, for example, the Signal protocol works. And there's a messaging service. Two users, Alice and Bob, want to look each other up on this service to get public keys for each other and start communicating. So in order to get these public keys, they actually have to query the server, which also has a database that maps, for example, phone numbers to public keys. By the way, we'll just use username, phone number interchangeably. So hopefully that's not confusing. And in a sense, what this makes the messaging service is not just a messaging service. It's not just running the Signal protocol, but it's also an identity provider. So now if Alice and Bob want to talk to each other, the first thing they need to do is get each other's public keys. So they look it up on the server. The server could respond with proper keys, or it could respond with a malicious public key to which it knows the secret key. And even though Alice and Bob think that they're communicating in a way that only the other person can read their messages, really the server is able to mount a meddler in the middle attack. And this is, by the way, assuming that the Signal protocol is completely securely implemented and there's no bugs and it works perfectly, encryption works perfectly. And what's even worse is that this actually can go undetected. So the solution to this, at least what I believe very strongly is the solution to this, is this transparent dictionaries model with some privacy. So identity provider holds a dictionary with username public key pairs. That is the case today. But and new users might join, and these users may then, for their username, update the public key. What they want, and this, by the way, is the guarantee that they supposedly get today, is that the server restricts queries to their username. So if I block somebody, they shouldn't be able to query my username and see if I got a new phone because my public key changed or something like that. The thing that we don't trust the identity provider for is that if the same username is queried at the same time, the server might actually give diverging values. And by the way, this is an example of a more general problem, and there are other applications that can find use for this type of solution. So one example is a centralized financial ledger, Kafka FTX. So there's a central server that's trusted for privacy and for ordering. So they're not going to just leak their entire database, but and they're trusted for ordering transactions, making sure that they maintain accounts and stuff, but they're not trusted for serving correct state, Kafka FTX. And some of you might even have heard of this type of setting, and the solutions therein may sound relevant to certificate transparency or tamper evident logging, but for various reasons, this setting has its unique challenges that are not just the same as certificate transparency. So you can't just defer us to the CT RFC and call it a day. So let's go back to key transparency. Remember, we have in this model an identity provider who holds a dictionary, as I said, as ad nauseum. This identity provider may cheat by showing diverging views to different parties. So what's the solution? Ideally, we want to prevent this identity provider from cheating altogether. But then this ends up actually needing assumptions on clients, specifically that they're good at storing long-term cryptographic secrets, which we all know is a big problem. And this also, by the way, is not an assumption that current systems make at all. So this would require a whole other kind of UI and thinking about those kinds of problems as well. So what can we do? What kind of security guarantee can we get that is closer in terms of user experience to what we already have? The security guarantee we go with is what we call anti-equivocation or non-equivocation. Basically, the server should not be able to show different keys to different clients without getting caught at some point. So at any given time, if Alice thinks her key is PK Alice, the server cannot get away with telling Bob that Alice's key is PK bad. One of these two parties is going to detect it sooner or later. And so given all of these requirements, let me just go through the model. By the way, this is going to be a very dense slide. Please bear with me, and we'll go over the most important points real quick at the end. So the first party is the identity provider, which stores this database and is trusted for privacy and authentication. So for example, if you log into WhatsApp using your phone number or into Signal using a password or something like that. And we want to eliminate trust for serving public keys. And by the way, all of the updates that are being made by users or users joining, all of this takes effect in discrete time steps called epochs. Just it's much more efficient to deal with it this way. And then there's users. Users join the system, then they might update their key. They might want to look up each other's public key if permitted. So you could go with a whitelist, blacklist, whatever type of model you want. That's doesn't matter. They want to check their own keys history up until the present time step. So like whatever changes were made to my key, I should be able to know. So which brings us to a guarantee that the users want, which is no changes are made to their key without their finding out. And correspondingly, their friends should receive matching keys for them. So again, what I said before, if Alice thinks her key is PK Alice, that's what everybody else should believe her key is as well. Now, there's a big white space there, and these are the two parties I've talked about. So now I'm going to introduce a third party, which we'll call the auditors. And these parties are basically just there to share some of the computational burden so that the users don't have to do very, very expensive computation, or the server doesn't have to do very expensive computation that adds latency for everybody involved. So these parties just check some global predicates, meaning that the server is making its updates in some sort of kosher way. So they could say between epoch start and epoch end, the server didn't delete any records. And this could be anybody, users, smart contracts, designated machines, TEEs, SGX, whatever you want, some unrelated do-gooders, if you will. And since it can be anybody, they actually should not learn data about particular users. Remember, we wanted the requirement that users want privacy. They don't want random people learning whether their public key is changing or even what it is, right? So given this model, I know this is a dense slide, just focus on the bolded text. We want to eliminate trust in the server for serving public keys correctly, and users want that all changes to their key are happening only with their knowledge, and everybody else sees what they're supposed to see according to that user. And auditors check some global predicates, but are basically completely untrusted otherwise. So with these high level details, some components fall out. So we need a mechanism for committing to a mutating database, and a mechanism to allow users to monitor their own public keys, and some source of ground truth. Like if you commit something and you want two people to have the same view, at minimum you want them to have some small string that they know is going to be identical. And also what we'd like, and this by the way fell out of my collaborators at Meta wanting to actually deploy this, we'd like to support billions of users. That's billions with a B, not an M. And not only that, we also want to serve users with computationally limited devices. Just because you cannot afford the newest iPhone 15 doesn't mean you shouldn't get the best security guarantees. So just again, recap of the model. Server has a database. They need to commit to this database. It's changing. There's a state that's mutating. And we need a way for users to access this commitment. So this is, in other words, this is the breakdown of the problem into two parts. And we'll talk first about committing and verifying a mutating database. So if you want a diagram, that's what I'm talking about. So there's actually been some work on this before Parakeet, and by the way, since as well. And the solutions are usually based on Merkle trees or some kind of vector commitment. And in our work, we use Merkle trees, and that's what we compare with as well. And the reason being that these require the least assumptions. And as a standards body, you know that nobody who's running a really large system would want to deploy things without standardized components. So to that end, that's what we use. And then they reduce user workload by either using third-party auditors, like I said, or they use cryptographic tools such as snarks or proof systems or something like that. And then for allowing users to monitor the history of their own keys, there are a few ways to do this. You could either use append-only authenticated data structures to prevent the server from cheating and then just erasing the evidence and being done with it. The problem with this is that no state changes are ever deleted. That's literally what append-only means. So that's one option. Or users must do linear work in the number of server epochs to monitor their own key. Essentially, it's kind of like assuming the user is always online because if they don't check certain epochs, the server might have cheated and they just get away with it. Or the server generates some sort of expensive zero knowledge proofs. So, okay, so I mean, it seems like all of these various components have kind of been solved, and this is a solved problem. So what are we doing here? It turns out, yes, in theory, we've solved this problem, but a lot of practical issues show up. And we've discussed several of these in the paper, but I will limit myself to 3 of them here. So the first problem I want to talk about is state machine replication. A lot of existing work just abstracts this away, and the experiments, they just used a single machine, and I know because I ran some of them. And that's obviously bad because at a global scale system, you're not going to have a whole bunch of servers that are basically represented by a single machine that stores a data structure locally. You just don't do that, right? So our work actually has a flexible storage layer API, which just allows you to plug in any existing database and just implement the requisite interfaces that are relatively simple. So that's all I want to say about that. The other thing, so the data structure for the state commitments, people had dealt with this before. And at the scale that we were looking at, this would grow to hundreds of terabytes over the course of even half a decade. And obviously this means that it's going to be too expensive to deploy, so it's harder and harder to convince anybody to do this work. So what we did is we replaced the underlying data structure to the following effect. So the orange line at the bottom, if you can even see it from the back, is the storage costs of our work over 5 years with 10 million updates. So that's users joining or updating their keys over 5 years. It's under 5 terabytes. And for a work that gets pretty much the same guarantees, called Seamless, and uses the same assumptions and everything, they ended up with 110 over 5 years, and this would just keep growing, right? So that's all I want to say about that. I want to go in a little bit more detail on users checking their own keys. So I mentioned earlier, there are 3 ways people do this. You either use zero knowledge proofs, you assume that users are always online or doing the equivalent amount of work to always being online, or you use append-only data structures. Each of these has its own pitfall. So ZKP is impractical for the server, always online is impractical for the client, and append-only data structures, well, they have ever-growing storage costs. And even with our optimized data structure and all that, and if somebody worked on it further and got it to be even better, I mean, that's all well and good, but try convincing somebody at a corporation to deploy something where you have completely uncapped storage costs with no way of doing any sort of garbage collection. So we basically come up with a middle ground, which we call secure compaction. So you basically say, maybe users don't have to be always online, but users that are actually using the system will come online at some point intermittently. And given that that's the case, maybe we can do append only, but to only an extent. And how do we do this? Let's go into a little bit more detail here. So think about this. So this is server epochs. So remember I mentioned the server is running in epochs and it's introducing batches of updates at every epoch. And say the server has had hundreds of thousands of epochs, so several years have passed. So everything that happened before epoch 1000, so 5 years ago or something, might be possible for deletion. It's just so old. So maybe you could just say, let's just delete anything that came before epoch 1000. Auditors just check that anything that's being deleted is old enough, however that is defined. But the problem is some of this old data may still be relevant and not all of it may be obsolete. So for example, if Bob didn't update his key in a long time, his most recent key was before the epoch where it's considered old enough, but it's still Bob's latest key, right? So it shouldn't be deleted. So maybe auditors check that only old enough entries are deleted and that for any deleted entry, there is some superseding entry that basically overwrites it. So it's actually obsolete, not just old. The problem is now this leaks data, metadata for particular users to the auditors, which we don't want to do as well, right? So, so instead what we say is let's involve both users and auditors and have some well-defined sparse epochs that only deal with deletion-related operations. And what we say is let's mark anything that is ready for deletion as tombstone and give a grace period to everybody to make noise to say if something tombstoned is bad. Give them a grace period or a checking period to whistle-blow about that. And auditors check that everything that is tombstoned is old enough, and correspondingly users check that only expired values for them might be marked for deletion. So anything that is marked for deletion for them is obsolete for sure. And then at the end of this checking period, so you make this period long enough so hopefully the user comes online at least once in this interim and then checks, and then after this grace period is over, you garbage collect. And yeah, and so that's how this model works. I won't go into detail for how this is all implemented, obviously. And I actually want to conclude my discussion about this commitment and verification for mutating databases part here, and go on to disseminating small commitments. So just as a reminder, you have this database that's committed, and users need a way to get this most up-to-date commitment as quickly as possible. Now, previous work on key transparency specifically places this problem just out of bounds. And then there's other work that seems pretty applicable. So for example, what if we use just existing gossip protocols? That might work, right? Users have some out of bounds communication mechanism and they gossip whatever commitment they get and share their views. The thing is that this is a problem for a global scale system where you might actually end up with partitions. Besides, users, remember, we want to support users who have very computationally limited devices as well, right? We want to be able to make sure that also if their internet is bad or they come online and just keep playing phone tag with their friends, they're still able to get these commitments and these corresponding cryptographic guarantees. So ultimately, the dissemination might be too slow. And even if the dissemination is pretty good, and the gossip protocol works pretty well, all guarantees in this are retroactive. So what is not retroactive? Blockchains. Blockchains are technically supposed to upfront check everything that's coming in, right? So you could post a commitment to a smart contract or in the op return field of a bunch of Bitcoin transactions that are they're predetermined somehow. But now you have to trust as a company that's deploying this, you have to trust the blockchain and its code, and as a user too. And by the way, even if you trust the blockchain and its code, the light plan solutions for this blockchain might be already too heavyweight. So you're letting go of the guarantee of trying to support very low powered users as well. And actually, prior work has shown that for any of the bigger blockchains, if billions, again, billions with a B, users query, you could end up flooding the network with just queries for key transparency and not let it do anything else. That does not seem like a good thing to do. So, okay, well, that is existing blockchain. So what if we just made our own blockchain? And blockchain means consensus. So let's just deploy our own BFT consensus protocol. So let's ask the question, do we actually even need everything that consensus provides? And before we even think about that, let's just see if we need to ask that question. So are there any pitfalls to consensus? Well, you have the n squared communication cost. So if you have n nodes in the consensus protocol, you have n squared communication, you end up with delays as a result of that. And by the way, this is notoriously complex to implement, right? As a slew of formal verification work on consensus verification has shown. So instead, we go back to the question, is consensus really necessary? So remember, the server is already trusted for compiling the updates and for finalizing the underlying database. The server already has infrastructure for compiling and serving messages from some sort of witnesses or quote unquote consensus nodes. So why don't we just use independent witnesses deployed by using TEs or industry consortiums or something like that? And these witnesses just need to store the latest commitment and check that the new commitment builds on it. So something like checking for a hash chain or something. And so how does this work? This is very, very simple. The identity provider creates a new commitment and just tells all of the witnesses, oh, I created this new up-to-date commitment that builds on the previous one you have. The witnesses check, and if this check passes, they just sign the commitment that they have now, the newest commitment, and return it to the identity provider, who just collects these signatures, maybe thresholdizes them or something or the other. But in any case, the identity provider collects these signatures, and next time a user makes a query, this goes together with the commitment. And a user basically just accepts if a threshold number of witnesses have signed this commitment. And by the way, let's look at the communication here, right? That was our big problem with consensus protocols. So now the identity provider communicates with the witnesses. This identity provider, by the way, is a big, powerful company that, or maybe semi-powerful, who already has servers to serve users. They also communicate with witnesses and users, but now the witnesses don't need to communicate with each other, which speeds things up considerably. And neither do they need to stand up the infrastructure to serve users, because users are not communicating directly with these witnesses at all. And besides all of these communication benefits, actually we get all of the same guarantees as BFT. So this is basically Byzantine fault tolerant, but you don't have liveness. And we depend on the server for liveness in the first place, so that doesn't matter. Giving that up is not bad in this setting. And it can be used in addition to other mechanisms. It's a simple protocol, easy to implement. I literally just explained all of it to you. It's pretty modular, so you probably get fewer bugs this way. And you can just use existing infrastructure and get certified commitments together with proofs and query responses. So everything, every guarantee that you get is basically simultaneous. And actually doing this in terms of consensus, you know that as the number of nodes increases, the latency is going to increase. And as our graph here shows, that is not the case for this very simple, reliable broadcast type protocol. And you can even have 80 millisecond epochs now if you want, so very quick updates. Well, at least this wouldn't be the bottleneck. The bottleneck would be the data structure side, which I talked about before. Yeah, and that is all I have I think I'm out of time also. So thank you.
You have time. You have time. All right. Thank you. All right. Does anyone have any questions for Jocelyn? Jonathan.
Hiya, Jonathan Hoyland, Cloudflare. Could you go back a slide, please?
Yeah.
Yeah. No, the one before that. Thank you. You say that the witnesses don't need to talk to each other, but if step 2 is a threshold signature, don't the witnesses need to communicate to produce the threshold signature?
I mean, as long as enough, it's basically like voting. So if enough of them vote by signing off on the commitment, it's fine. And you can thresholdize any signature and any like regular signature as well, right? You can just like show as your knowledge proof that all of these signatures verify, that like 5 out of
Okay,
7
it's
verify.
multi-sig rather than threshold sig.
Yeah, except you have, it's not that you require everybody to sign off. As long as the majority signs off, you're done.
Okay, very interesting. Thank you.
I guess my question is, obviously the identity provider is someone like Facebook or whoever, presumably. Who would run the witnesses?
Yeah, so this would be something like TEs could be one example of using witnesses. You could use, for example, an industry consortium, assuming they don't collude with each other, or there's incentive not to collude with each other, something like that, or there's regulation that prevents colluding with each other.
Right, they'd have to be someone independent to the identity provider.
Yeah, indeed, yeah.
Okay. All right, does anyone else have any questions? We've got a couple of minutes, if there are. I see Siobhan in the text, in the chat, posted a link to the Keytrans group. So if people are interested further in this work, I guess that would be a good place to go.
Yeah.
And one on Monday and one on Friday. So we're making anyone interested in that topic stick around all week.
Yeah.
All right, last call for questions. If not, thank you. Thank Jocelyn again. All right, so that is the end of this session. I think there's 3 fantastic talks today. I think all of them demonstrate the sort of very applied nature of the work and how we can have some really interesting protocol design work and measurement studies and so on, which translate into very practical results, which are useful for the internet and hopefully applicable to the standards community and improve the internet as well. So I think 3 great talks there. We have a couple more of these talks in the meeting in Dublin. So if you're in the Dublin meeting in November, look out for those. And after that, we will be opening the nominations for the next year's prize. So start thinking about any great applied networking research you've seen to nominate for next year's awards. Please do come to the rest of the IRTF sessions later this week, to the Applied Networking Research Workshop tomorrow, and thank you again to all the speakers. Thank you, everybody.